Okay, welcome to Organic Chemistry, Chapter 7, Part 3. Okay, so Part 3 is going to be the last chapter for the semester. So we're going to talk about proteins. Okay, talk about proteins. So what are the objectives? Objectives are identify the characteristic part of alpha amino acids. Okay, so we're going to talk a lot about amino acids. Okay, draw the structural formula to illustrate the various ionic form of assumed by amino acids. Write reactions to represent the formations of peptides and proteins. Explain what is meant by primary structure of proteins. Describe the role of hydrogen bonding in secondary structures of proteins. Describe the role of side chain interaction in the tertiary structure of proteins. And describe the conditions that can cause protein to hydrolyze or become denatured. Okay. So you must understand this is the amino acid is something like the monosaccharide. Okay, so it's the basic unit. Okay, amino acid is the basic unit to form proteins. Okay, so amino acid and amino acid, they're going to form peptide bonds and join together to form a functional proteins. So we're going to start by looking at the structural and chemical properties of amino acids. So what are amino acids? Amino acids is an organic compound that contains both an amino groups and a carboxylate group in ionic form. Okay, so you can see from here they have amino groups. All right, then they got H. You can actually draw the H up here if you want. Okay, just to make it easier, instead just draw H. Okay, here is the carboxylate COO minus, okay, or COOH. This one can be COOH. This one can be NH2, okay, really depending on conditions. Then here we got the R group, yeah. The condition that we spoke about is pH, yeah. pH can change this group, yeah. So this one is a basic, you can draw that, okay, so you can draw NH3, COO minus, then the R group. The R group is the only one that is different between the 20 amino acids, yeah, okay, the 20 amino acids, the R group is the difference between them. So you more or less, the other three groups over here, these three is all the same, yeah, okay. So just to clarify first, the behavior of amino acids when it's not joined together to form proteins, it has a slightly different behavior compared with when the amino acids are joined together through peptide bond to form proteins. Okay, the reason is being that these two groups, the amino group and the carboxylate groups, one is joined through peptide bonds, the behavior will be different. It no longer is a amino group or carboxylate groups. Instead, it's a peptide bond, yeah, okay, so the behavior is going to be different. So the R side chain of amino acids, okay, that impart chemical individuality to the molecules. So the functions of the amino acid is largely depends on the R groups, okay, the behavior of the R groups here. The R groups can be, out of the 20 amino acids we have mentioned just now, they can be divided into these four groups here, okay. They can be divided into, the R group can be divided to either neutral and non-polar side chain, okay, which means that there's no, neutral means no charge, okay, and non-polar, as you know, that it can be due to, it's not polar basically, okay, side chain. Neutral, okay, no charge, but polar side chain, or basic side chain or acidic side chain, yeah. Basic side chain is when they can accept, okay, they can accept hydrogen ion, whereas the acidic, they can donate the hydrogen ions, yeah, okay. Usually in this case, right, the basic side chains are amino groups, either NH2 or NH3+, okay. The acidic one is either COOH or COO minus, yeah, okay. These are the two common basic side chain, and this is the common acidic side chain, yeah. So here you go, out of the 20 amino acid, that categorized as neutral and non-polar side chain are all these, like glycine, alanine, valine, leucine, methionine, proline, phenylalanine, isoleucine. You can see their side chain over here in the circle. Okay, this one is representative. You can see that there's no charge. Okay, and it's not polar. Basically, it's a hydrocarbon chain. Yeah. Then we have amino acid with neutral but polar side chains. Okay, they are able to form the hydrogen bond. Yeah. Okay, like for example, you can see from here threonines, asparagine. You got the carbonyl group. You got the hydroxyl group. Yeah. Then the acid that is basic. Okay, you can see there's a NH, NH3, NH2, NH2 plus. Okay, all these are a representative of the basic polar side chain. Then we got the acidic side chain, the CO minus. Okay, so these are the 4 groups of amino acids. Okay, 4 groups of amino acids that can be categorized out of from the 20 amino acids. Yeah, and again, just to illustrate, these side chains are the one that dictates its functionality. Yeah, okay. So for amino acid as well, it has a stereochemistry. Okay, it has 2 forms, the L form and the D form. Yeah, the L form is when the amino groups is on the left side. Again, this one is not just simply draw it per se. Okay, it will be based on the Lewis structure. Okay, that you draw it. Okay, in basically this has been converted from the 3D molecules here. So from 3D molecules, okay, based on the concept that has explained previously, then they are rotated in such a way when you converted, it will converted, and if the NH3 is on the left side, it's a L amino acid. If it's on the right side, it's a D amino acid. Yeah. But for the living world, the one that we consume as well, we make in the body is the L form. Yeah. So amino acid, as you can see from here, they have these 2 sides. Okay, don't talk about the R group first. Okay, these 2 sides, you can see from here, they actually can be ionized. So what happened, right, is that over here the hydrogen can actually be transferred to the NH. Okay, one transfer, what happens? Here becomes CO minus, here become NH3 plus, okay, which is basically shown on here. Yeah, so this is the one that is the one that usually forms, okay, and what we call zwitterions. Yeah, zwitterions. Okay, due to internal acid-base reaction between these 2 groups here. Okay, so for the zwitterion, okay, we don't talk about the R groups. Okay, we assume the R group is neutral. Okay, so when we talk about this, when this is neutral and this happens, the net charge of zwitterions is 0. Okay, net charge is 0. Okay, because amino acid zwitterions, they form white crystalline solids with very high melting point. Okay, the high melting point was due to the plus and minus here. Okay, basically they can form with another amino acids through what we call the ionic bonding. That's why they have a high melting point here. And because of the charges as well, has a high water solubility. Okay, just like the sodium chloride. As I mentioned before, you can actually change the charge due to the change in environment. Yeah, the pH of the environment. A change in the pH, okay, the environment can actually induce a change in the charge. When in the acidic condition, okay, acidic condition, when there has a surplus of hydrogen ion, okay, surplus of this, what happens is that it will be added to these 2 groups, but here is full already. Okay, the maximum is NH3 plus, so it will be added to here to form COOH. You can see from here they form COOH here. Over here, there's no surplus of hydrogen ion. In fact, it's deprived of hydrogen ion. So instead, this will actually take away whatever hydrogen ions here. So the base will take away the hydrogen ion. Take from where? it cannot take from here anymore. It will take away from here. So when you take away from here, what happens? It will be converted into NH2+. Okay. So always remember, yeah, the pH can actually change the charge of the molecule. Okay. The one way is through the basic and the acidic charge group. Yeah. So this is the changes in pH also affect the acidic and basic side change, but not the neutral ones, okay, as I mentioned before. So in this case, right, when they change the R groups, okay, the R group can lead to a total change of the Zetriones here. So instead, it can be a net negative or net positive, okay. So that is not a property of Zetrion. Zetrion is when we don't consider the R groups, we only consider the NH3 and the CO minus form a net zero charge here. When the R group come into place, okay, we don't call it as a Zetrion, okay. Then the R group may have effect on the overall charge here. The effect can be leading to the whole amino acid to obtains a net negative charge or a net positive charge. Okay. When the pH is down to the point where the amino acid have no net charge, this is called what we call the isoelectric point. Yeah. So always remember, yeah, no net charge doesn't mean no charge. Yeah. No net charge means that there's charge, but because it just neutralizes here, because there's a equal amount of positive and negative charge there, so there's no net charge. Okay, and this is what we call isoelectric point. Actually, isoelectric point can have some effect to overall system here, because when there's no charge, okay, like what I have explained in the Kanji 101, when no net charge, what happens? The emulsion droplet can no longer repel, and so they can start to stick to each other, yeah, and lead to coalescence of flocculations. So each amino acid has a unique isoelectric points. Those with neutral R groups, okay, those with neutral R groups are all near a pH of 6. Okay, when there's the neutral R groups, but when the R group is basic, okay, then the isoelectric point will be higher. So for example, is in 9.47, then the lysine will reach a net zero charge here. Whereas like aspartate with the acidic R group, then when you reach about 2.98 pH, okay, the amino acid has no net charge, okay. And this can be basically when you lead to no net charge, okay, it can have a lot of effect on the solubility, okay. Usually it can lead to precipitations, yeah, precipitations when there's no net charge. Either there's no net charge or near to no net charge, the precipitation will start to form. Okay. This is how you draw the structure of amino acid leucines. Okay. All right. In acidic solutions, okay, acidic means they have surplus of hydrogen ions. So what happens? This one will be filled up. Okay. Here no effect. So it will convert to COOH. You can see from here, there's no effect here. Whereas in basic solutions that is deprived of hydrogen ions, the basic solution will absorb or will steal away any of the hydrogen ions. Steal away from where? It cannot steal away from CO minus, so it steal away from NH3 plus to become NH2. Yeah. Okay. This is exactly of what we have mentioned in field side early on. Okay, let's select some of the amino acid and discuss further. Yeah. Okay. Those that are some of the amino acid that are in special case. Okay. In the case we got what we call cysteine. Cysteine is very special because of this SH group in the R group. The R group has this what we call sulfhydryl groups. Okay, sulfhydryl groups SH, and this R group of the cysteine. Okay, this is the basically R group. The R group of the cysteine molecule is special in the case that when it meet another amino acid, the cysteine amino acid, the SH group can actually be oxidized to form what we call disulfide bond. This disulfide bond is a covalent bond, so which means that once it's formed, it's not easily broken. Okay, and this disulfide bond, later on you will see that it's very important to stabilize the tertiary structure because it's a covalent bond and it's not easily broken. Okay, and you can use it to hold the tertiary structure. Then the amino acid and amino acid, as I mentioned, it can actually join together between amino acids. Where they join through the carboxyl group of one amino acid with the amino groups, okay, to form what we call a peptide linkage or peptide bond here. Okay, this peptide bond you can see is made of C double bond O and H. Okay, you can move over here. Yeah. C double bond O and H here. Okay, so this one is basically the peptide bond. So you can see from here, as I mentioned before, one is formed peptide bond. What happened? They loses the functionality of a carboxylic acid group and the amino groups. Okay, there's no more charge as well. You can see from here, there's no more charge, and it's joined together to form a larger the amino acids, the peptide bonds. Yeah, the peptides. Okay, form a larger peptides. Okay, draw the full structure of the following tripeptide glyval. Okay, as you can practice more in the tutorial question as well. So you will see from here how you draw. Basically, you find out the 3 amino acid that is mentioned here. Then after that, you will join the carboxylic acid group and the amino group between the amino acids and form this C double bond O and H here. So and H you can form here. Okay, so you can see one peptide bond and then another. Okay, another peptide bond here. The N and the C join together here. Okay, so peptide bond. Okay, so you form 3 amino acids here. So this is how you can draw it as well. Not necessarily draw the 3-dimensional structure here. Okay, so basically we have learned about the amino acid. Now is the time to actually learn what happens to when the amino acid and amino join together to form what we call peptide or a proteins here. So now we go into the structural and chemical property of proteins. So proteins can have various sizes. It can be very, very small and it can be very, very large. As you see from here, insulins, there's a 600U, the U unit here we learned from chapter 1 and 2. Okay, and then it can be as large as 800,000 U. Of course, it got something larger than that. Okay, so you can see from here, the size got to do with the number of amino acids joined together. The more amino acids joined together to form, okay, then it has a larger molecular weight. Solubility of the proteins here. The tendency for large molecules such as protein to remain soluble in or form a stable colloidal dispersion depend on the pH of the solutions here. Okay, usually what happens, right, is that the pH, as I mentioned before, okay, that it can affect, the charges of the amino acids. But when I just go back over here, what do you see? Once joined together already, right, this, okay, the peptide bond is no longer affected by the pH. Okay, of course, you will have one N terminal and one C terminal. This is basically at the beginning and the end of the polypeptides. What happened, right, is that the pH, you can see, is largely going to affect the R group. Okay, if the R group has those charged R groups, okay, either positive or negative, okay, or the acidic or the basic side chain, then it can be affected by the pH changes here. Okay, and I can tell you now is that the proteins, okay, most definitely they have this kind of the amino acids with the basic or the acidic side chain. Okay, just the difference, right, is that whether they have a lot or very little, okay, of these amino acids. So when the protein molecules are at the pH when they take a form that has a net positive or net negative charge, the presence of these like charges causes the molecule to repel one another and remain dispersed. And because of this net positive negative charge, they can remain soluble in the solution. Okay, the solution can be water or something else here. Alright, so as I mentioned before, when the pH change to such a way that the whole molecule has net zero charge or very near to net zero charge, what happens is that they will lose their solubility and start to precipitate. Okay, so this is basically all tied out together to what I have mentioned earlier, yeah? Okay, let's look at the proteins. Before I go into the structure of proteins, first of all, you must know that the proteins are usually obtained either through plants or through animal sources. Okay, proteins like, for example, milk proteins, you have casein, you get whey proteins. For egg, you got egg proteins and so forth. Okay, where the protein come from, you learn from the Kanji 101, the cell biology. It actually comes from the DNA of the organisms. Okay, for example, the milk. Okay, because the cows has certain DNA. Okay, they can produce the milk proteins. Okay, so the DNA produce the proteins are produced based on the DNA sequence of the organisms. Okay, so that's why you won't see, like, for example, canola can produce milk proteins. Okay, because it doesn't have the DNA, so it cannot. All right, unless you play with the genetic modifications here. Okay, otherwise you cannot get from there. Okay. So the structure basically is obtains, the proteins are actually fixed already, okay, and usually is based on the DNA of the organisms, okay. So the structure of extremely large molecules, like for example proteins, are much more complex than those of simple organic compounds. Large proteins molecule consists of a chain or twisted and fold into a complex three-dimensional structure which also impart a unique functional properties in biological system. Okay, what are the system? Storage functions, catalytic function, protective function, structural function, movement function, and so forth. Okay, movement function, for example, like actin and myosin that I learned before. Okay, so as I mentioned before, DNA, you obtain protein from animal or the plant sources. Usually all these proteins, right, why it has been made in the organism or the plant or animal is because these proteins will serve a certain function. Okay, you serve a certain functions that the functions will, like I mentioned, storage, catalytic, and so forth, or more than that, yeah. Okay, and because of that, we can actually exploit human actually obtain from there and exploit the biological system. Yeah, like for example, we can obtain the proteins from the papaya leaves. Okay, to obtain this enzyme called protein enzyme called the papain. Okay, as you have learned from the Kanji 101, the papain can cleave the muscle fiber, yeah, okay, provided that they are folded in a certain manner. Okay, they are folded in a certain manner. Okay, the folded structure is fixed already, but the environment, okay, as I mentioned, the pH molecule can change the folding. If the folding change, then the function will diminish. Yeah. So the folding, right, can be categorized in a few levels. Primary structure is just a sequence. Okay, so the amino acid based on the DNA, it will be like the sequence, alanine, okay, is in a fixed position already. This is what we call primary structure. From primary structure, they will be folded into a secondary structure, alpha helix, beta sheets. Then they're going to fold it into more complex structure called the tertiary structure. Yeah, the tertiary structure will give a certain function. Okay, the folded into primary structure is like the telephone wire, the olden times one. Primary structure you can see straight. Secondary structure you can see they fall into a very simple three-dimensional structure, and tertiary is more complex structure folded here. Okay, so you can see from here primary structure. All the protein have a, okay, you can find the primary structure here. You can learn that later on. Okay, like casein, which is the milk proteins, they have a primary structure as well. Okay, depending on where it obtained from, they have a slightly different sequence. Second structure is actually second structure is folded in more of a slightly more complex, and it can categorize either as an alpha helix or beta pleated sheet. If it's not in these two alpha or beta pleated sheets, then we categorize as a random structure here. Okay, this very important here. Please note this here. When how they form into alpha helix and beta sheet, there have to be a certain interaction. The interaction is due to the interaction between the peptide bond. Okay, you can see from here, this one is basically the peptide bond of one of the amino acid with another peptide bond of another amino acid. They form what we call the hydrogen bonding here. So looking at this, you can see from here, round about 4 amino acid away. You can see from here, this is one amino acid, one amino acid, and so forth here. So you can see from here, this amino acid, they will form, okay, the peptide bond over here. Very important, yeah. Remember the peptide bond, yeah. The peptide bond, the C double bond of the peptide bond will form a hydrogen bond with the peptide bond of the other one, the NH of the another peptide bonds of another amino acids. Okay, they form the hydrogen bonding over here. Okay, and so forth. This one will form with another one down there, and so forth. The distance, right, is about 4 amino acid away. Yeah, about not really 4, about 3.6 amino acid away. Okay, from one another. So if you calculate 1, 2, 3, 3.4, about 4 amino acid away. Yeah. Okay, to be exact, it's about 3.6 here. Okay, the distance is about 3.6 amino acid away. They form another the hydrogen bonding. So because of this hydrogen bonding, they form into a, you can see here, a alpha helix structure. Okay. The beta sheet is exactly the same, just that it form into the sheet wise. Okay, it will form into the sheet wise. Okay, same thing. The sheet is the interaction between the peptide bonds, the carbonyl group C double bond O with the NH. They form a hydrogen bonding here. Okay, the distance can be a lot further, yeah, for the beta sheets, yeah. Okay. So this is basically a schematic diagram showing the secondary structure of a protein. You can see from here there are some alpha helix, there are some beta sheet. Okay, all the other some doesn't form. This is what we call a random structure. Yeah. Folding into this is second structure is one way. Okay, of a function. Of course, some proteins, right, they will fold into a more complex structure. Okay, as I mentioned, the structure will give you a certain function. Okay, the change of the structure, then the function will diminish. Okay, so they will fold into a tertiary structure. This tertiary structure, right, is due to the interaction between the R group of the amino acid. The secondary structure is due to the interaction between the peptide bonds, okay, forming hydrogen bonding. The tertiary is largely due to the R group. Okay, the R group, like for example, the R group with they can form the disulfide bridges. Okay, a covalent bond that I show you, I've mentioned before, disulfide bond or disulfide bridges. Okay, disulfide bond or disulfide bridge, bond or disulfide bridges. This is covalent bond, so it's very strong. If you form this, the whole structure is going to be very stable. Yeah. Okay, then they can form salt bridge. Salt bridge is through charges, hydrogen bonding. Okay, between H and O or H and N and so forth. Hydrophobic interaction is through the hydrophobic R groups here. So you can see from here, their demonstration, the interactions over here, disulfide bridge, covalent bonds, then the salt bridge, then the hydrophobic interaction, then we got the hydrogen bondings here. All these are the one that use it to stabilize the tertiary structure, okay, tertiary structure. Okay, so what kind of R groups between this and this? What is it? Interaction, hydrophobic. This and this, they can form hydrogen bonding. This and this with the charge, they form salt bridges, yeah? Okay, it's very important for you to realize that the protein is folded in such a way. If you see a lot of the proteins, right, usually their natural environment, right, is actually water. So they are folded in such a way, right, that the hydrophilic regions will be outside of the proteins. Okay, the hydrophobic will be inside. Yeah, usually if the protein is made and suspended in the aqueous-based or water-based environment, okay, which is in the cell, okay, usually the hydrophilic one will be outside. They will fold in such a way that most of the hydrophobic one will be in the core of the proteins, yeah, okay, because as I mentioned, the hydrophobic doesn't like water, so they would remain in the middle of the core, yeah, most, not all, yeah, most. Okay, so we have talked about the protein structure, okay, how it's been folded. As I mentioned, the structure is very important for functions. Okay, so now let's talk about hydrolysis, okay, the breakdown of the protein, or another term called denaturation. Denaturation, both of these actually destroy the structure of the protein. Because of this, it can lead to an alter of the function or a destroy of the original function of the protein. Okay, remember that, yeah? The original function will be destroyed, okay, and or it will lead to a limitation or reduced functionality, depending on the degree of hydrolysis and the degree of denaturation. Hydrolysis is when you break the amino acids, okay? How you break it, you can use acid or base, you can use enzyme to break the peptide bond, okay? The time you give to hydrolyze, it can lead to smaller. The more time you given to hydrolyze, then if you break more and lead to formation of smaller peptides, okay? Smaller peptides. Of course, the temperature and the pH can affect as well. The higher temperature, the more extreme acidic pH can lead to higher degree of breakdown of the peptides, yeah, the peptide bonds. Whereas if you're looking at denaturation, denaturation is not hydrolysis. There's no breaking or very limited amount of breaking of the peptide bonds, okay? Denaturation is due to a change in the environment leading to unfolding of the proteins. Okay, like for example, you can see from here, it unfolds into a random structure. At first, it got some alpha helix, but now it becomes random. Okay, so okay, this can be due to a change in the temperature, can be lead to exposure to physical and chemical conditions, can be caused by pH and so forth. Okay, so denaturation is due to the unfolding of the protein. Obviously, the unfolding lead to the diminish of the original functions. Okay, because the exposure, it leads to a lot of different interactions, especially as I mentioned, when they fold, the hydrophobic is normally inside. But once unfold, what happens? All these hydrophobic groups can start to interact with another unfolded proteins. Okay, when they interact more and more, what happens? Interact, yeah, not react, yeah. When they interact more and more, what happens? They form an aggregate. It's just like the egg white proteins when you undergo heats. Okay, the egg white lead to denaturation. The denatured proteins coagulates to form a white egg white, yeah. Okay, a white egg white. So again, please don't confuse between denaturation and hydrolysis. Yeah, hydrolysis is a breakdown of the proteins through breaking of the peptide bonds. Denaturation has very, very limited hydrolysis, okay, or none, and mainly is due to unfolding. Okay, the unfolding is due to the disruption of the is due to the disruption of the interactions that use it to stabilize the tertiary structure here. Okay, for example, this one, I just go back to the slide. So when this interaction has been disrupted, for example, the addition of salt can affect this. Okay, the heat can actually break that. Okay, then this one, because of the kinetic energy by heat, it also can affect these two. Okay, when it's disrupted, what happens? Then they will unfold. Yeah. Of course, after this already, then if you go further, then it can affect the secondary structure and so forth. Okay, tertiary can be affected, secondary structure can be affected. Yeah. So you can see from here, once affected, they unfolded. Once unfolded, they expose all the unnecessary group, lead to a precipitation or interaction between the denatured proteins. So these are some of the conditions that can lead to denaturation: heat, ultraviolets, organic solvents, strong acid base, detergents, heavy metal, and so forth. Okay, so I'm going to stop here. Okay, so this one will be the end of the chapter for this semester. Okay, so if you got question, please ask in the Padlet. If you got no question, please indicate no questions. Okay, for attendance marking. Okay, thank you so much.